Check if audio is working. Somebody from home, can you hear me? Do you hear? Anybody connected? Can you hear me? Okay, now, before I start, I would like to say one thing again that I already said yesterday. What I saw is, again, that most people came in the first laboratory group yesterday, and then few people in the last, and few people today. Now, this is not going to work. Why it's not going to work? Because if I check at the people who came today and the people who were there yesterday, I know that I went to check what they were doing, and I had to fix problems with the code for most of them. So I'm sure that when you come in the first block, when everybody comes in the first block, those who come in the first block will have the same issues in the code. If you are 60, 70 people like usually, then I cannot check what you're doing, then I cannot fix your code, and the errors that you make now, you will keep adding them, keeping them and adding to them until the end of the course. Then at some point, nothing will work anymore, and you will not be able to understand why things are not working, which means that you will not be able to do the project part. Now, if this happens, and you keep coming all in the same laboratory, then of course you can't expect to complain that you're not able to do the laboratory, that you don't understand how to do things, that things don't work. Because the proper way, if you want to be followed, if you want to allow me to check what you're doing, is that you come in the slot you have been assigned to. I've already done the work in a way to avoid that always the same people end up in the least appealing slots. This requires efforts from everybody, requires efforts from you, effort from me that I have to follow you, of course, but if the effort doesn't come from you as well, then you will not be followed as much as required to understand, to actually do properly the laboratory and the project part. In the end, who's going to give the exam is you, it's not me. So if you're not prepared for the exam because you don't follow what you are asked to, and you are asked to do that in your interest, then you can't complain that you do bad in the exam part, in the exam. So having said this, again, follow the schedule, because already with this week, there were several problems already with this laboratory. The coming one will be harder. So at some point, I will not be able to answer and to check what you're doing. Already yesterday, I had the time to check and speak with 5 or 6 people, because the answer takes some time with the complexity of the things we're doing. If I have 60 people and I'm able to check the work of 5, 6, 10, then out of those 60, maybe 30 will be okay, maybe 40 will be okay, there will be 20 who need assistance, they don't realize they need assistance and they won't get it. And then at some point they will realize they needed assistance, but then it's too late because we are too far in the program, okay? So if you don't follow this schedule, it will hurt your performance. Okay. With this said, we can start with today's topic. Okay. Now, yesterday we started seeing probability. Again, this part, if you have questions, ask, but I went quickly because these are things that maybe you don't remember because you studied them some time ago, but are things that in some sense you should already have seen. And the way you have seen it, maybe it's not exactly the same, but it's enough for the way we will use them. So even if we don't go into all the mathematical details, it's not this part, we don't need all the mathematical details precisely what I said yesterday. So this was meant to be a recall of things that you hopefully already somehow know, maybe in a more or less formal way, but more or less you know the idea behind. Today we will start, hopefully, we will finish this revision, and hopefully we will start with things that you may not have studied that we will actually need for our machine learning course. Other questions on what we saw last time? Are you, I don't say you remember everything, but do you have already a rough idea of what we were talking about, like cumulative distribution function, probability mass function, probability densities, and so on? Okay. Now, one thing that where we stopped yesterday was somewhere around here. We defined the density of one possible way to express the density for a random variable, and essentially we said how we map the densities to probabilities that a random variable takes a value in some interval. For a random variable, it makes sense to ask what is the probability that a random variable takes a value in some interval, and that's obtained by taking the density and integrating over the interval. For example, if this is the density, the area below the curve between A and B is the probability that X takes a value inside the interval A and B. And in general, I may have more complex than just intervals, but for us, intervals would probably be enough. Actually, we will never compute integrals in any case. Now, one thing that you may or may not, and in any case, if you have not, it's important for us, is the concept of random vector. Random vector is an extension of random variable that essentially consists in considering jointly multiple random variables and arranging them in a notation that is the same notation of a vector. So we consider a set of m random variables, and we consider them, we write them as if it was a vector using a vector notation. That's just a graphical notation, but it's easy for us for the moment to use the vector notation. Then we will treat this as a vector afterwards when needed. These random variables have a joint density. That is, we can define the cumulative distribution for all these m random variables. That is nothing else than the probability that the random variables are jointly lower or equal than a given value. Yes? Okay, sorry. Thanks. Okay, you should see. In any case, I was introducing the concept of random vector. We take our m random variables, we stack them in a vector, and then we can define the cumulative distribution function for the m random variables. How? We consider the joint cumulative distribution, the probability that the first random variable is lower or equal than x1, the second is lower or equal than x2, and so on, at the same time. So essentially, if we have two random variables, we compute the probability that the random variable takes a value in this region of space, this coordinate 1 and the coordinate 2 of my random vector. And we will write in a random vector notation, in a vector notation, this, we'll write it as f of vector x1 to xm, these are values, so small x. That's the cumulative distribution that the random variable will take a value inside this region of space. So the probability that the random variables are all lower or equal than the correspective value. Let me check from home, everything is working, yes. Now, this defines the cumulative distribution for the random vector. So the random vector is nothing else than a collection of random variables for which the cumulative distribution function is defined as a function of a vector that corresponds to nothing else than the joint cumulative distribution for the different random variables, where the values that I'm computing the cumulative at are the components of the input vector of this function. Now, this defines the distribution of the joint distribution. Then once I have defined the joint distribution, I can also define the distribution of the single components So I can talk about what's the probability that the first component is lower or equal to a value. If x is a component of a random vector, this probability is also called marginal distribution, because it's marginal in the sense that it's the distribution of just the component x1 when I take out the influence of the other components. So the joint distribution tells me jointly for a vector what is the probability that all the components of the vector are lower or equal than the corresponding value. The marginal for random variable j tells me what's the probability that that random variable is lower or equal to a single value. It's a density. This is a one standard density, standard cumulative distribution function. It's just that if x is a component of a vector, we call this marginal distribution. Now, for discrete random variable, the joint distribution will be, we can define also the joint distribution density. Well, for both, we can define the density. For the random variable that are discrete, this will be the joint probability mass function, which is the probability that given a vector of values x1 to xm, all the random variables of the vector take exactly the values inside the vector. And it's related to the cumulative distribution by the same expression that tells me that if I want to compute the cumulative at some point, I need to sum up all the contribution of the densities for values that are in the region of space bounded, in the left lower region of space bounded by the value I'm computing the density at. Sorry, let's make. If I have my density that is defined in space, I will sum the values of the density over this region that will tell me what is the cumulative distribution. For random variables, we have that a possible density is obtained by computing the partial derivative of the cumulative with respect to all the different variables, and the cumulative is obtained by integrating the density in the same region. In this case, the density is continuous, so we will integrate the density in the region of space defined by, whose boundaries are defined by the values in x. Then the marginals are defined in a similar way, but they can be obtained from the joint density by integrating with respect to the variables that we are not considering. So for example, if I have two components distribution function, so let's write it in this way. I have a random vector with two components. So what's happened? Okay. With two components, x1 and x2. This is the cumulative and this is the density. Then the marginal for just x1 is obtained by integrating. Let's write it like this to remember that this is the joint for the two variables. Is obtained by integrating the marginal with respect to the component that I'm not marginalizing with an over, that I'm not keeping. So if you want, in a notation where the random vector is written explicitly in terms of its component, I take my joint, in the case of 2, I have just 2, and I integrate with respect to the variables that I'm not taking the marginal for. So all the other ones, I'm taking the, if you want, okay, this is the definition of marginal. Again, we will not compute these integrals, we will just say use the marginals with no results when we need. Now, for random variables, we can also define the conditional density, that is the density of a random variable when the other random variable takes a given value. It's defined similarly to the conditional probability, It's the joint density for the two random variables divided by the marginal of the one we're conditioning on. So if we condition on random variable y taking its value small y, then the distribution of x, given that y is small y, is obtained by the joint density computed at these two values divided by the marginal for y computed at small y. Bayes' rule applies also to densities. It tells us that the conditional for y condition on x times the marginal of x is equal to the joint. So the joint can always be expressed as a conditional times the marginal of the one we're conditioning with respect to. So when we have a joint density, and now when it matters, I will represent a random vector as a vector. When the vector representation is not relevant, I will just list the random variables inside the function. So this can be a random vector if you want. In any case, the joint density of two random variables can always be expressed as a conditional density, where I'm conditioning on one of the two, times the marginal of the one I'm conditioning with respect to. So in this case, I'm conditioning on x, so I have y given x times marginal of x, which means that I can also write it in the opposite way, which means that these two quantities, since they are both equal to the joint, are also equal, from which you get, as long as the marginal is non-zero, you get Bayes' rule that tells you that for all the values x and y which are in the support of x, for all the values of x for which f of x is non-zero, then the class conditional of y given x can compute them from the conditional of x given y using this expression. I take conditioning on y, multiply by marginal with respect to y, divide by marginal with respect to x. Now, one thing that is important is the concept of conditional independence. We have statistical independence is defined. We say that two random variables are statistically independent if the cumulative distribution function can be factorized as a product of two cumulative distribution, each depending on the single random variable, which for discrete quantities can also be expressed that two random variables are independent if and only if the density can be expressed as the product of the margin. The joint density corresponds to the product of the marginals. For the continuous, it's a bit weaker. We can say that if the density can be expressed as the joint density can be expressed as a product of marginal, then the random variables are independent. The opposite is not true in general, because we can find densities for which this does not hold, but for which the random variables are independent, but the decomposition doesn't hold. But these are specific cases that we will not really use. In any case, if my density can be factorized, then the random variables are independent. Conditional independence is the same thing, but conditioning on some value of a third random variable. If the cumulative distribution of x and y given z factorizes over x and y, then x and y are said to be conditional independent given z, and vice versa. Conditional independence essentially means that once we know one of the two variables, that doesn't tell anything to us about the other one. So two variables that are independent, if we know the value of y, we have no additional information on what are the possible values of x. Essentially, conditional independence tells also us that if x and y are independent, then the distribution of x given y is the distribution of x, because y does not influence x. Conditional independence tells us that y does not influence x if z is known. If a third value z is known, then knowing also y does not give us any information on x. So this is the concept. Then we can define, again, here I hope these ones are already known, the concept of mean or expected value. For discrete random variables is the sum over the support of the value x for which I'm computing the sum times the probability of that value x. So this, for discrete random variable, is the probability that x takes a value. For example, if I roll a die, I have 1 with probability 1 over 6, then I have 2 with probability 1 over 6, and so on. The average is 3.5. The expectation of the value that I get is 3.5. For continuous random variable, it's obtained by integrating over the support of the random variable, so those points where the density is non-zero, x times the density function itself. This gives me the concept of average value, where the average is taken by considering all possible values of x, each weighted by a contribution that is proportional to the density function itself. We can define the variance as the expectation over x of x minus its mean to the square, which we can also express as the expectation of x squared minus the mean of x to the square. And the expectation of x squared is nothing else than the same expression, but this time I have here x squared instead of x. So it's an average of the value x squared, where the probability for density is weighting how much each element should contribute. So for example, if this is my density, let's say this is 0, then this point will contribute a value 1 multiplied by the density value. In an integral form, it will be that the small interval around this 1 will be weighted by this height of the density. In a discrete case, I consider different values, each weighted exactly by the probability that that value is taken by the random variable. As we have seen for the empirical covariance, the variance measures a spread of the values of the random variable around the class mean. That is, if the random variable can take values that are far from the mean, then the variance will be large. So for example, a random variable where values that are far from the mean have a large chance of being observed will have a large variance. A random variable for which the values that we observe are mainly close to the mean will have a small variance. So the variance measures how spread my points can potentially be with respect to the class mean. The standard deviation is defined as the square root of the variance. We can generalize this to the kth moment of a distribution by simply computing the expectation of x to the power k. And we can define the centralized moment as the kth moment of a distribution where I removed the mean of my distribution from x. This is the equivalent of a center distribution. I center my distribution around the mean of the distribution itself, and then I compute the kth moment. The variance is nothing else than this for k equal to 2. In general, we define the expectation of a function of a random variable as the, let's look at the continuous one, as the expected value of the function of the expected value of what I obtain by transforming x through that function. So that means that, let's look at the discrete one. For each value of x that I can observe, I will apply my function g of x and then compute the average of these transformed g of x values, where the average is weighted by the probability of the corresponding x. So for example, if I roll a die, let's not roll a die because let's roll a die, and I want to compute the expectation of the logarithm of the value that I roll. I will take the logarithm of 1 weighted by the probability of 1 plus the logarithm of 2 weighted by the probability of observing 2, and so on. So I take the logarithm of the values that I can obtain, I average them with a weight that is given by the probability that I get the corresponding x. And for the continuous, I do the same, just that the average is done in a continuous way, so it becomes, rather than a sum, an integration where the weight is given by the density. You can imagine that this is like a sum of contributions that are very small, that are the x small, so infinitesimally small contributions that become an integral. We can extend to random vectors this concept. The expectation of a random vector is nothing else than the expectation of the components of the random vector. So we simply compute the expected value for the different components. This is a result that we will probably use, but I will recall when needed. Expectation is linear, so if I have a random vector and I apply a linear transformation, this defines a new set of random variables, because I have x1, x2, and x3. Then I will have y1 that is the combination, a linear combination of the first of x1, x2, x3. Then I have y2 that is another linear combination of these, and so on. I will define 3 new random variables. Then the expectation of these random variables is obtained as the same linear transformation applied to the expectation of the original random variables. And the same, if I have a random variable that corresponds to the sum of 2 other random variables, the expectation of the result is equal to the sum of the expectations, each taken with respect to the random variable that I am considering. Now, in general, we will not write explicitly the random variable whose density we are using in the expectation, because typically that's clear from the context. We write like this when we need to remember that here I'm taking integral with respect to the density for x. But here I'm integrating the density for z. Remember that this is a function, it's a distribution for x. This, I still use notation z, but it's a distribution for z. Here the name of the random variable tells me that these are 2 different functions. This is the density function for x, this is the density function for z, which may be different. Now, when we have 2 random variables, we can define the covariance of 2 random variables. That is, the expectation of xy minus the product of the expectations of the 2 random variables. When the covariance is 0, we call the random variables uncorrelated. Now, if x and y are independent, then the covariance will always be 0. Independent random variable have a covariance 0. The opposite is not true. So, if I have covariance 0, that does not mean that my random variables are independent. That holds true only if random variables have a specific distribution. In general, this is not true, and it's fairly easy to build random variables for which this does not hold. But what holds is that if they are independent, then they are also uncorrelated, and we will use this next week. We can also define another thing that is called Pearson correlation coefficient, that is a normalized version of the covariance. It's the covariance divided by the standard deviation of x and y. Well, is this interesting? Because we can show that this value you have it here, the absolute value of this is always greater or lower or equal than 1. So the 2 standard deviations act as an upper bound on the covariance of the 2 random variables, which means that the correlation is 0, then the covariance is 0. If the correlation is 1, that means that y and x are linearly dependent. That is, 1 can be expressed as a linear transformation, a scaling plus a constant of the other one. So knowing 1 tells everything about the other one. Once we know the value of x, we have complete knowledge on the value of y. So the Pearson correlation coefficient tells us that if we are 0, then the close to 0, then the random variables are almost uncorrelated. If we are close to 1, then there is almost perfect correlation between the two. So it measures the way, how much two random variables change in a similar way. This means that they change exactly in the same way. If I increase x, provided that a is positive, I increase also y in a similar way that is just proportional to how much I increased x. Now, we can extend this to a random vector. For a random vector, we can define the covariance matrix as the expectation of x minus its mean times x minus the mean transpose, which I hope it's not surprising given what we've seen up to now, will give us a matrix that contains on the diagonal the variance of the different random variables, and outside of the diagonal, I have the pairwise covariances of the components of the random vector. This is the analogous of what we had when we were computing empirical covariance matrices. With empirical covariance matrices, we had on the diagonal the empirical variance of the data, and outside the empirical covariance of the data. For a random vector, we have a similar object. We have a covariance matrix that is defined in terms of expectations, so it's an expected value. These expected values are on the diagonal the variance of the component of my random vector, and outside of the diagonal I have the pairwise covariances of the random vector. Notice that this matrix is symmetric. What I have here is here, what I have here is here, and so on, because the covariance of x and y from the definition is equal to covariance of y and x. The product is commutative, so if I replace the role of x and y, I get exactly the same result. Okay. And last thing, as for the variance, we can express it as an expectation of xx transpose minus the product of the mean transpose. And again, this is something that for the moment is not particularly important. What's important is that it's symmetric, it's positive semi-definite, so the eigenvalues of the covariance matrix of a distribution will always be greater or equal than 0. And if I have a linear transformation of a random variable, I hope this is not surprising, and again, the covariance matrix transforms in a way that is the same way that empirical covariance matrices were transforming. I pre-multiply by A and post-multiply by A transpose. So the covariance matrix of Y can be computed from the covariance matrix of X and the value A of the linear transformation. Now, some notation before we move to the relevant part. We'll denote the density using symbol typically F with the random variable we are defining the density for written below, and then this will be the value at which we are computing the density. So this is the random variable and this is the value. If it's discrete, we may use directly the letter P for probability, because for discrete, the density corresponds to the probability that the random variable takes that value. So we may write it directly in this way. For conditioning, we will either write in this way or put the conditioning directly below, depends on the context. When the density depends on values y that are not random variable, we may either write it twice or write it only once for discrete. But notice that in this case, we write it twice to remember that we are conditioning on a known value. From the mathematical point of view, we are not really conditioning. We just use an abuse of notation to remember that it's the density defined in a different context. Remember that conditioning does not define a different event. Conditioning defines a different measure of the probability that some events will happen. So it's just defining a new function f for the random variable x. And then for discrete quantities, we may also write in this way, probability, the condition is the probability that x is equal to small x, given that y is equal to small y. Or if y is not a random variable, Again, we use the same notation as conditioning because this is the equivalent to defining a new probability density when we assume something. When we refer to non-distribution, we will typically use a symbol that refers to that distribution. The symbol will be used to define both the distribution, so the normal distribution with mean and variance, whose density will be defined with the same symbol, is a function of x that depends on the parameters of the density. So this will be the distribution. We may say x follows a normal distribution. And if we need to define the density of that random variable, we'll use again letter n. This is the normal density computed at value x. Now, let's start recalling some of the distributions that we will need for the course. Other questions on this part? Is this part at least partially known or something that I can rely on? You will manage on your own. If you don't remember, you studied it in any case and you are able to revise it? Yes or no? Okay. Okay, so now we start with the part that interests us. The first distribution that we will consider is the Bernoulli distribution. The Bernoulli distribution models what? Binary events. You have for sure seen the example of tossing a coin head or tail. We see that for us, this binary event will be labeling a class when we have a binary problem, class 1 or 2. So the Bernoulli will be important because it will be a model for our class labeling when we discuss probabilistic models. But for the moment, let's stay with the head and tail example. From the mathematical point of view, we will assume that the random variable takes two values that are 0 and 1. We may call this tail and head. We will, when which is 0 and 1 is not relevant, we will say head and tail. But from the mathematical point of view, when we need to discuss about the density, it will always be value 0 or 1 for us. So we have a random variable that can take value 0 or 1 that can represent two outcomes of a possible experiment, like head is 1 and tail is 0. The distribution of x is called Bernoulli, and it's defined how? Well, we can define it's a discrete random variable, so we can define it by giving the discrete probability density function. We have only two possible ways, so we just need to provide the value of the probability for these two possible ways. The Bernoulli distribution has a parameter p. The parameter p is the probability that I get value 1. In this case, the distribution is defined, is parameterized by value p, that is the probability that I get head, or more exactly, the probability that my random variable gives 1. Now I need to exhaust all the cases. What is the probability for x being equal to 0? Well, the probability must add up to 1. So here I cannot give whatever value I want. If p is the probability that I observe 1, then 1 minus p must be the probability that I observe 0, because the two must add to 1. Now, this is how you define the density. In this case, enumerating all the possible outcomes and giving a value to that. This defines our density. It is a parametric density because it depends on the value of p. For a fair coin, p will be equal to 1/2. There is the same probability that I observe the same value. For a rigged coin, well, it depends how I rigged it. It may be 0.3. I made the coin such that if I toss it several times, only 30% of the times I will get a head. That depends on the problem we're talking about. We have a parametric model. The density for this parametric model is often written in this way because that's more easy to work with mathematically. In which sense? In the sense that since x can only take values 1 and 0, you can observe that as long as p is different from 0, you will always have that if x is 1, this will be p to the power 1 times 1 to minus p to the power 0, so it will be exactly p. If x is equal to 0, what I have is this expression, which is 1 minus p. So whatever the value of x that my random variable can take, this is the expression of the density. If p is 0, we take the 0 to the power 0 is also 1. So we take the limiting of x to the power 0 when x goes to 0, which is 1. This is a compact way, and it's useful because I don't have to consider separately the cases. I have a single expression that holds for all values of x, which we see is useful when we need to use the distribution. Then we can generalize the Bernoulli to the binomial distribution. The binomial distribution is doing what? It's essentially counting if I repeat a binary trial n times, how many times I will observe value 1. So if I toss the coin several times, how many times I observe head. If p is the probability that a single toss will give me head, and I assume that the tosses, once I know p, are independent, then the binomial will tell me what is the probability that I observe exactly n times x times the value head out of n tosses of the coin, when each toss of the coin has a probability p of giving me head. Now again, notice that we have a similar expression to the Bernoulli. Indeed, if we plug n equal to 1, we get exactly the same distribution. The Bernoulli is the same as the binomial when n is equal to 1. The number of success that I have if I toss the coins one time is exactly the probability that I get a single head. Indeed, Bernoulli is a special case of binomial. If I have n Bernoulli that represents n independent tosses of the coin, the binomial is exactly the sum of the Bernoulli. Remember that the Bernoulli is 1 when I observe a head and 0 otherwise. If I sum, I get the number of times I observe a head. So it's exactly a binomial density. And then here you have other quantities that, if needed, we will see. You can define the mean is p and the variance is this one, but that's not important for us. Second set of variables that we will, the distribution we will need, this we will use for multi-class classification, is the categorical and multinomial distribution. The categorical is the extension of the binomial to multiple possible outcomes. For example, when you roll a die, you have 6 outcomes. In general, k. In this case, we assume that these outcomes can be labeled as 1, 2, 3, 4, up to k, so we give a progressive number to the outcomes. Then we say that if the x can take one of these k outcomes, we can define a vector p that tells us the probability of each outcome, and we say that the random variable follows a categorical distribution. The categorical distribution is defined by giving for all possible outcomes the value p of the probability. So for example, for a dice that is rigged, so it has not always the same probability of giving the same face, I can enlist for all possible outcomes probability of 1, 2, 3, 4, 5, and 6, then this defines my categorical model. I have vector p of values, that is the parameter of the distribution, and the density function is defined by what? It's exactly this function. When x is equal to 1, probability of x equal 1 is p1, probability of x equal 2 is p2, and so on. Of course, this requires that the sum of the pi is 1, because these represent the probabilities of all the tosses, so they must add up to 1. So the categorical distribution is nothing else than the distribution that we use to represent when a random variable has k possible outcomes, and we define it as a function, as a density that is a parametric density, where the parameters are exactly the value of the probabilities of the different outcomes. Now, we can represent it in this way. The probability of x being equal to small x is the value of the probability vector corresponding to small x. Here you see the probability that x takes value 2 is P2. The probability that x takes value 1 is P1. Now, one way to write this density is as a product over all probabilities. Well, okay, this one I think we can skip. Let's see this one. Now, a convenient way to represent the same quantity is, well, you see that here the problem is that if I want to express the density for a value x, this x will act as an index of a vector p of possible values, which is not easy to work with. When x is just an index inside a vector, it's not easy to work mathematically with this quantity. So the standard way of defining the categorical distribution is just give the 6 values of the probability of the 6 outcomes that I can have is not practical when I need to work with it mathematically. So what we do now is give a different representation of the same information in a way that at the beginning may look much more complex, but in the end we will see it's much more practical to work with. That is, we have up to now represented our outcome, the tosses of a die, as a value in 1, 2, 3, 4, 5, 6, the value that the random variable can take. Now let's do a different encoding. We say that we define a random vector x that is what? If the die rolls 1, then the random vector will be a vector that contains 1 in the first position and then zeros in the remaining position. The outcome 2 is encoded by the vector 0, 1, 0, 0, 0, 0. Outcome 3 is encoded by the vector 0, 0, 1, 0, 0, 0. So you see there is a mapping between our outcome and a vector that encodes that outcome. How it encodes the outcome? The position of the 1 is the index that corresponds to the outcome that I observed. So here outcome 1 means that 1 is in the first position and the rest is 0. If I roll a 2, then I will represent it as a vector that has an element 1 in the second position and everything else is 0. If I roll a 3, I will have a vector where the 1 is in the third position and everything else is 0. Why is this? Because now I can define my density in terms of the random vector x being equal to one of the 6 possible encodings. These encodings are called 1 out of k encodings because I have k positions that are all 0 except 1 that is 1. And of course I have 6 possible encodings because these are the 6 possible outcomes. I can represent it mathematically as the probability that the random vector will take one of the possible 6 encodings with an expression that can be written like this. If I have vector, so for any vector x, this x here is one of the encodings. So for example, if I observe the roll 2, that's the probability that the vector 1, the vector x is equal to this vector, we can show that we can express the density as a product over all possible values pi. Remember that p is the vector of the probability of the different rolls. So for example, if it's a fair die, all these will be 1 over 6. If it's a rigged die, maybe these will be different values, and so on. Product over all pi to the power xi. Why? These are the components of the vector that I'm computing the density at. These are all the values of the probability, but remember that when I run this product, all these values do what? Well, I take my vector of probabilities, I take my 1 out on k encoding, and at each iteration of this product, I take 1p to the power corresponding element, which means that if I have this encoding, what I have? p1 to the power 0 times p2 to the power 1 times p3 to the power 0, p4 to the power 0, and so on. Result, p2. This is selecting exactly as result the result of this is P with the index that corresponds to the original encoding of my outcome. But when I represent it mathematically, I have a vector that acts as a basis, a vector that acts as exponent, and then I just need to multiply them. We will see that we will work with the logarithm of the density a lot. The logarithm of the density is a sum of xi logarithm of pi I, which means that what we will work with will be the logarithm of these probabilities, which will be multiplied element-wise with the vector that encodes the outcome, and then I just need to sum. When I need to do this on a machine with a library, or when I need to do the development of finding what is the optimal value for P, working with this expression as a function of P is much more easy to work than if I had to write P of 3 times P of, when I have P of x1 times P of x2 times P of x3 and so on, where these are the outcomes of the different random variables that I observe. So we will see that it looks more complex now, but it will allow us to write our expression that we need to manipulate in a much easier way. When we need to manipulate them, it will become much easier. Questions? Okay, then we can extend the categorical to the multinomial. And here again, it's useful to start from the categorical expressed as 1 out of k encoding. The multinomial is, I repeat, n trials, where each trial can have 1 out of k possibilities. So I roll my die several times, and then I count how many times I get 1, how many times I get 2, how many times I get 3, and so on. So I will have a vector that tells me I got value 1 2 times, I got 10 times value 2, I got 15 times value 3, 3 times value 4, then 9 times 5, and 1 time value 6. These are the outcomes of rolling the die. You make the sum of these, and that's the number of times that I rolled my die. The multinomial tells me if each toss can be described by a categorical described by vector p, then the probability that I observe exactly these outcomes out of the n rolls that I have is described by this expression. And notice again that this expression, forget about this, we will see that this for us is actually irrelevant. The core of this expression is this, which looks extremely similar to this. So the core is, we'll have the probability pi to the power xi, where xi is the number of times I observed the outcome I. So, for example, in this case, I have probability of tossing 1 to the power 2 times probability of tossing 2 to the power 10 times probability of tossing 3 to the power 15. Notice that if I have a single toss, this vector will contain exactly a single position that is 1, because if I toss the roll die only once, I will have only one outcome that is observed, and is observed only once. This is exactly the categorical expression for the 1 out of k encoding that we introduced earlier. So the way we represent with a 1 out of k encoding also shows us that the categorical is nothing else than the multinomial when n is equal to 1. And actually we can show the opposite. If we have n times we roll a die, and each time we encode it with a 1 out of k encoding, so the first time we roll 1, then the second time we also roll 1, then the third time we roll 3, this is 0, 0, 1. Then the sum of these vectors will be what? Will be the number of times I rolled 1, the number of times I rolled 2, the number of times I rolled 3, and so on. So if these are independent categorically distributed samples represented with a 1 out of k encoding, their sum is a vector that represents the number of times that I observe each outcome, which follows a multinomial distribution. Questions? Okay, the other distribution that we will work with is the Gaussian density, the Gaussian distribution. It's also called normal distribution. And in this case, we are moving to the continuous world. The Gaussian distribution is a continuous distribution, and it's defined, well, we define it by the density. Actually, it should be defined by the cumulative, because we've seen that the density is just, we have multiple densities, but for us, it doesn't matter. We define it by the density, even if it's not 100% correct. It's a random variable which has this density, which you should know, I hope, is a bell-like shape. It has two parameters. One is the mean, and the other is the variance. Probably you have been used to parameterize it by standard deviation and mean, but forget about the standard deviation. We parameterize it by mean and variance. Actually, we will not even use the variance when we need to estimate this parameter, but the variance is the square of the standard deviation. So what I write here is always the variance. What you see here as the second parameter will always be a variance. The mean corresponds to the peak of the distribution, and the variance tells me how spread it is. Sometimes we will parameterize it in terms of the inverse of the variance, which is called precision, and in this case, we will write it like this. Lambda is the precision, so what I see here is always the variance. The variance is equal to lambda to the power minus 1. This is called precision, and we see why working with the precision is more useful. When mean is 0 and variance is 1, we call this standard normal distribution. So standard normal is the red one that you have here. The mean moves the peak, the variance controls the spread. Larger variance, you see there is more spread. Points that are far from the mean are more likely. Lower mean, the spread is smaller. And we can see that when the variance decreases, the height of the peak is also becoming taller. Why? Because for any of this curve, the area below the curve must be integrated to 1. This is a density. So if we get the range smaller, we need to increase it to make it taller for the area to remain constant. And this is actually what we will use to, what allows this to for us to make inference when we use this as a classifier. Exactly the fact that these peaks and the fact that the shapes of different distributions are different. But we will see this, of course. Let's skip this. Now, one thing that we will need is to extend the concept of Gaussian density to random vector. So Gaussian density, again, I assume that you have seen, because it's impossible if you have done a probability course that you have not seen the Gaussian density. But probably you may not have seen the multivariate Gaussian density. The multivariate is the generalization of the Gaussian distribution to random vector. Remember that random vectors for us are sets of random variables that we arrange as a vector. So let's consider a random vector whose components are x1 to xn. And let's assume that these are independent and they all follow the standard normal distribution. IID means, but we will see it again, independent and identically distributed, which means they are independent and they all have the same distribution. So all of them are Gaussian, standard normal, and they are independent. If this happens, then we say that the random vector follows a standard multivariate normal distribution, and we can show that the density is what? If they are independent, we can express the density, well, since they are independent, we can express the density as a product of densities, which implies independence. We define the joint density as a product of the marginals, and we say that these random variables jointly are a random vector that follows a multivariate normal distribution. So we define the density in terms of the product of the marginal, which is consistent with our assumption that they are IID, and then we can compute explicitly the density is obtained by computing the different marginals and multiplying them together. What is the expression for the density of a Gaussian random variable is this. For a unit-varied random variable, we have some constant term that typically will be of little interest. Then we have the, let me write like this, the precision, this is the 1 over square root of the sigma square is equal to the precision, because this is 1 over the variance, which is the precision, times exponential of minus 1/2 the precision x minus mu square. This is 1 over sigma square is again 1 over the variance, which is the precision. Now the important part, sorry, this is a k not of x, it's just k. It's a constant that does not depend on x or the Gaussian parameters. The important part of this expression is here. Now what happens when lambda is 1 and mu is 0? That becomes some constant that I don't care about, exponential of minus 1/2 x squared. So this is the standard normal density. K is just a constant that we need to remember. Yes, we need to remember it's the constant that ensures that k times this integral is equal to 1. The value of the constants typically are kind of uninteresting. Which means that if I need to compute this, what will I have? Product of k exponential of minus what? xi to the square. Each component of my random vector, each random variable, gives a contribution that is some constant k times exponential of minus xi squared, the standard normal density, which is some k prime exponential of minus 1/2 sum of xi squared. I bring the k's, all the k's outside. So here I will get k to the power n, if you want. And again, I don't care what this value is. Then I have product of exponential is obtained by moving the product inside the exponential, but it becomes a sum when I move it to the power. So it becomes a sum. What is the sum over I of xi squared if x is a vector whose components are the xi, so the xi are the components of a vector? What is this? Is the norm of x squared, which we can write as x transpose x. So if x is the vector for which I'm computing density at, my density will have this form, some constant exponential of minus 1/2 x transpose x. And we say that if a random vector has this density, then it follows a standard multivariate normal distribution that we write in this way. Then we can extend to the general multivariate Gaussian distribution by defining a random vector x if I have a random vector y that is standard multivariate normal distributed, and I can express x as a linear combination of y, then we say that x follows a multivariate normal density, multivariate normal density, we just write n, where this is the mean of the distribution, and the covariance matrix of the distribution, and we see why we call this covariance matrix, is A transpose. We will call this covariance matrix, we will see why it makes sense to call it covariance matrix, because we will see that the covariance matrix of this x will be equal to A transpose, so for this reason we call it covariance matrix directly. Those are the parameters of the distribution, and the density can be obtained, and I will not prove it, by applying the rules for the transformation of the random variables that tell us how to compute the density of a function of a random variable from the density of the original random variable. We can show that the density has this form. Or, more precisely, writing it as a function of the inverse of the covariance matrix, it will be some constant k, determinant of the covariance matrix to the power minus 1/2, exponential of minus 1/2 x minus mu transpose lambda x minus mu. What does this represent? Well, these parameters represent the shape of the distribution. The distribution will have a bell-like shape. Here you see the example for a two-dimensional random, multivariate random, normal distributed random variable. The first case is the standard one. The mean represents the position of the peak. Here you have a plot where you see the 3D plot of the density, and below what are called the contour levels of the density. What are the contour levels of the density? Imagine that you take this density and you slice with planes that are horizontal with respect to the input axis, okay? So the vertical axis is the value of the density, and here I have the two components of the x1 and x2 of my vector. As a function of x, which is component x1 of x2, I will get a value for my density. Contour levels are what? If I slice my, doesn't like this slide. If I slice my density plot with planes that are parallel to the x1, x2 plane, I will get that these intersect the density at different points. If I slice at different levels my density, I will get different sections. So if the level is on the x-axis 0.03, I will get this section here. If I slice it at a larger level, 0.12, I will get this slice here. Then I can plot for different levels what are the slices. This corresponds to the set of points that have the same value of the density, and the value of the density is equal to what you see here. So if I slice my plot with a plane that is at height 0.03, I would get that the points that have this density lie on this circle. Now we can see that the mean is at the center, so you see that the distribution is symmetric. Contour levels are symmetric, so there is a symmetry in the density. The mean corresponds to the peak, and then we can see that the variance controls the shape of these contour levels. First of all, let's observe that these contour levels have what kind of shape? What kind of shapes you see there? Geometrically, what are those shapes? Ellipses. If you remember at the beginning, we said we will represent covariance matrices with ellipses, and then I will explain why. Now, this is why. Why? Because the contour levels of a standard normal distribution with a given covariance matrix correspond to ellipses. And the values of the covariance matrix control exactly the axis and the length of the axis of these ellipses. In particular, if the covariance matrix is the identity, it means that I will observe circles. If the covariance matrix is diagonal, what will I obtain? Well, once more, those are ellipses. They have principal axes. Ellipses have principal axes, in this case 2, the principal one and the second one. What are these axes? Well, these axes correspond once more to the eigenvector of the covariance matrix of the corresponding distribution. So if we slice our density with planes, we will obtain ellipses. These ellipses are oriented in which way? Along the principal components of the covariance matrix of the corresponding distribution. In this case, you see that I have a diagonal matrix, which means that the eigenvectors of this matrix are 1, 0, and 0, 1. So they are the principal axis of my space. And indeed, the axes of these covariances are aligned with the principal axis of the plane. Here you see that there is a non-zero correlation, which means that the eigenvectors of this matrix will be oriented in this way, which are the axis of the ellipse that you have here. What does this represent? They tell us that these two random variables tend to change in a similar way. If I increase one, then also the other will tend to increase. This is represented by the correlation. The correlation is positive. From the point of view of the ellipses, there is a direction over which there will be a large variance, a large change of the two random variables, and a direction over which there will be low change. What does it mean? Again, it means that they are correlated, and the axis of this there is a correlation which we can see from the covariance matrix, and this correlation is related to how the distribution is oriented. The distribution is oriented in this way. In this case, it's oriented along the diagonal of my space, because there is a correlation in this direction for the two components. When I change x, also y will tend to have a similar, not identical because correlation is not one, but it will have a similar change. The two tend to change in a similar way, and the distribution becomes squeezed along this direction. Okay, I think I said everything. Questions about this? Yes. What do you mean, previous plots? Hmm? We can, but we will see that that's not how we select it, and we will see that LDA does not correspond to this model, but to a specific version of the model. You will get all these answers in the next lectures. So I will not anticipate, because it will be anticipating things that I will say in any case. But yes, this will be related to the LDA problem, and we will discuss how to actually select the threshold based on considerations similar to this, but we will see how in the context when we get to that. But the intuition, yes, is in the going in the right direction. Okay, questions up to here? Okay, then the next thing I will do in the last 10 minutes, I hope that I would do more, but let's see for the next week how to organize it, is now we want to estimate the density. So we have defined up to now densities which are parametric. We can define a Bernoulli distribution with parameter P that represents the coins toss. And we said if we know P, that models a coin which has that probability of giving head. Now we have the opposite problem. We have somebody who tosses a coin, and we want to get the value of P because we don't typically know the value of P. That is a density estimation problem. We have some observations. For the moment, let's keep it discrete. Several tosses of a coin. We want to get an estimate of the probability that the coin will give head. We don't know if it's unbiased. If we know that it's unbiased, we know the answer is 1/2. But we know that it may or may not be biased. So we need to understand whether we should bet on head or tail. We don't have access to the coin. All the thing that we can see is somebody tossing this coin n times. How can we get an estimate? Now, the answer is trivial in the sense that we see that if you tell me the trivial answer is I count how many times I get head, then we will see that that is one possible answer. Under some assumption, it will be the correct answer. And then we will discuss also that that answer is typically not enough in some cases, but we will not open the parentheses. But let's do it formally, because for this problem, it's easy to find the direct answer. For some other problems, it may not be trivial to find what is the answer for the problem. So let's try to formalize this, that is an intuitive solution, in a way that allows us to recover a similar or even better result. We model everything as random variables. We have observed tosses. Each toss will have an outcome that is, for example, the sequence head, tail, tail, which we map to values. So 1, 0, 1, 1, 0. We interpret these as outcomes of random variables. Each toss is associated to a random variable that can give a value in 0, 1. Our goal is to do what? Let's formalize it properly. Our goal is to predict the probability that the next toss, the one we want to bet on, will be head, given that all the previous tosses are known to have given, for example, head, tail, head, head, and tail. So given on the value that we observe, we want to compute what is called the predictive distribution that tells us what is the probability that I will observe ahead given the history that I have observed. Now we need a way to define this probability. Now we cheat. We have somebody who knows the answer to the problem already. It tells us the probability of head is pi. Now, it's trivial. The next probability will be pi. This is the intuition. How do we formalize? Well, let's for the moment assume that we know that the probability of head is pi. We need to make some other assumption. We assume that given this knowledge, and we will see that it's important that we say given this knowledge, the coin tosses are independent and identically distributed. Why given the knowledge? Because if we don't know this, then seeing tosses give us information on the next one. The more we see head, the more we change our idea that the coin is rigged towards head. So the coin tosses by themselves are not independent. The coin tosses are independent once we know that the probability of a single coin given head is, for example, 0.5. If we don't have this information, we cannot directly assume that the coins the tosses are independent. And actually they are not, because every time we see an additional toss, we get some information on what could be the probability that we observe ahead for the next one. So they are not independent per se, they are independent given that we know the probability of a single toss. So there is this hidden piece of knowledge that if we know it, then we can consider the toss independently. Once we know that each toss is a probability of 30% of giving head, then the history will not influence the new tosses. So they are independent. Knowing what happened in the past becomes irrelevant, but it becomes irrelevant if I know this value. So this is the idea. Tosses are independent and identically distributed. That means that each toss will have the same distribution as all the others, so it will not change during time the probability with which I observe head. Whether I observe it in the next toss or in 2,000 tosses from now, it will always have the same probability, pi. And if I know pi, the history will not give me any more knowledge on the next toss than what I have already from knowing pi. How we can model our tosses? Well, we can model each toss as a Bernoulli distributed random variable with parameter pi. Each toss can give value 1 or 0, which means that each toss is a probability of giving 1 that is pi, and the probability of giving 0 that is 1 minus pi. So it's a Bernoulli distribution with parameter pi, yes? I don't understand. Which one is more than one? No. This pi? No, this pi is a value between 0 and 1. It must be between 0 and 1 because it's the probability that I get one head. No, it's free in the sense that we don't know its value, but since it's a probability, it must be constrained between 0 and 1. We don't know it, but it must be a probability. So whenever we don't say something, we assume that the parameter space we looked is only those that are allowed. So in this case, I didn't say it, but pi must be between 0 and 1 because it's the probability of observing a head. We don't know its value, but for sure it's between 0 and 1. But we need to find its value in any case. We need to find what is the value of pi. So we model our tosses as if they are Bernoulli distributed with parameter pi between 0 and 1. For the moment, we assume that somebody told us the real value of pi, so it told us a value that is for sure between 0 and 1. Now, since we know from all these things that once we know pi, all the random variables behave the same way and the history does not influence the next toss, then also our next toss will be modeled as a Bernoulli of pi. So xt being equal to head given x1 to xn and pi will be exactly pi. So let's put 1 because we assume that head is represented by 1. But this probability will be exactly 1 because the history will not influence the past, so I can remove the conditioning except pi, and then I know that given pi, xt has a Bernoulli distribution with probability pi. So this is exactly the probability of the next toss. It makes perfect sense. If I tell you the probability that the next toss is pi, then pi is the probability of the next toss. The problem is that we don't know pi, and now this is where things start becoming a bit more complex. We need to find a way to estimate pi. We will follow a frequentist approach, so we assume that there exists a true value of pi that was used to generate the tosses. So we follow the frequentist approach. The probability is a result of repeated experiments where there is a true probability distribution that is responsible for generating the tosses. We already discussed why this is not a good solution in general, but we will see it's the simplest approach that we can take. So even if I don't like this approach from a philosophical point of view, let's assume that there is this distribution that is responsible for generating the values because it's simple to handle it. The problem is we don't know this. This is exactly the quantity we want to compute. So we will estimate it. How? Well, a possible way to estimate this value is to define a function that tells me, okay, let's consider all possible values for pi. If pi is equal to 0.1, what is the probability that I observed the sequence head, tail, tail, head, tail if pi was 0.1? What is the probability that I observed this if pi was 0.2? What is the probability that I observe the sequence that I have observed already if pi was equal to 0.3? So if I consider all possible pi's, I can answer if I assume that the true parameter pi has some value, then I can compute the probability for the tosses that I already observed. This function is a function of pi. It's called likelihood function. The likelihood function is the probability of the observed values given the model parameters, and it's a function of the model parameters. Whenever I plug a value of the model parameters, that will give me an answer that is the probability that I observe my dataset if the model parameters were really those that I passed to the function. Now, here is a case where I'm conditioning, but this is not really a random variable. The maximum likelihood approach tells us to look for the function parameter pi that maximizes the function. What is it? It's the set of parameters under which my observed dataset is most probable. So I will select the parameters that best explain, in a probabilistic way, the observations that I have, that best explain my dataset of previous tosses, under which the probability of the previous tosses is highest. So we will look for the maximizer of this function, and we will do it next time. Okay, questions? Okay, then for today it's all.